My name is Venkat Bhethanabotla. And Mandek Richardson refused to come here because he's too busy writing his dissertation, and Samuel Morrill got a job, so they sent me. So this talk is going to flow quite well with the previous one. I hope to show that there could be some other details of value. It's combining the metal-enhanced fluorescence or the plasma-enhanced luminescence, which was just presented by Aaron, with acoustic waves to perhaps give a few more advantages in sensing. This is the goal. So I will pick this immunofluorescence, a very simple technique which is not with high limits of detection, and I will try to show that maybe we have a chance of making it useful. And the metal-enhanced fluorescence in our results in how to enhance the signal, and then the surface acoustic waves and what role they have. So currently, the quick answer here is that immunofluorescence is a very easy technique where you have antibody-antigen binding on a surface. You can do this biomarker quantifications, but unfortunately, it's not very sensitive, so everyone does ELISA, and they're in between a number of techniques. So you can see how it works. Basically, you have an antibody-antigen. You can have another layer you can add and enhance, increase the amount of signal, but they become indirect and get more complicated. Even so, there are some problems which we will address. They are the detection limit too high, photo bleaching, so autofluorescence from other things that may interfere, overlap from other proteins that cell fluoresce, maybe blocking. It's very time consuming in terms of how long it would take. So our objective would be, my goals would be to improve this immunofluorescence to see if we can go to this sort of concentrations, nanograms of proteins per milliliter. So then the one part is to use the metal-enhanced fluorescence just discussed. The other part is to bring a surface acoustic wave device to remove these non-specifically bound proteins which interfere with the signal, and perhaps reduce the length of the assay. That's the deal. This says about the same thing really, what I said a couple of seconds ago. In metal-enhanced fluorescence, there was a little bit of it alluded in the previous talk. You can play with the enhancement factors, like here I have 141 on this fluorophore, 23 on this fluorophore, which is the largest, with some mixed particles of silver, copper. Silver has very high radiative decay, so we look for that. And some time ago we have shown that you can do several things like mix the metals, sizes, shapes, and many people have shown this. So in this case, it is annealing to overlap with two different types of fluorophores, producing two different levels of enhancement. So in this work, we have taken, the previous talk again explained that it's hard to produce regular arrays of features on the scale of 50 nanometers or so, which are really what are needed for enhancing fluorescence to factors we would like to see. But Zhang in Yunnan Zha's group out in Georgia Tech now, they have come up with some solution techniques, and these again aren't the best. They produce particles in solution using a polyol process. You can make very nice silver cubes. These were tuned to 50 nanometers to 488 for the Alexa 488, and this result summarizes what you can see without any interfering proteins. There are no proteins that interfere with the signal. This again a fluorescence microscope measurement, a simple way of measuring this, as mentioned before. This process the image. You can see past a concentration of 1 microgram without any enhancement, you just get nothing. But if you put some silver particles carefully, spin coat them in this case, you can get down to 1 nanogram quite easily, and this is representing 1,000 times enhancement in the lowering of the detection limit. So this slide just gives the details on how the particular experiments I showed in the previous work were done. They are results of 3 measurements. And this graph shows the quantification on a scale, concentration, intensity through the microscope versus concentration. So you have a lot of room to work with this. Then the next part of the work talks about how do you deal with this non-specifically bound proteins which interfere with this fluorescence signal. So we use surface acoustic waves and the phenomenon of acoustic streaming. So surface waves that are, you can create this little device, a surface acoustic wave device between interdigital transducers. This is where you would have your sensing region, and this would be the shear vertical component. So this substrate is, you're seeing this way, but if you see this way, you have motion like this. Displacements are really small, on the order of maybe even angstroms, nanometers, angstroms actually mostly. Those kind of things are, when they are in the air, they would be very regular. You can make a device that's quite low loss, but when they hit a liquid, they get converted to leaky surface acoustic waves through the phenomena called acoustic streaming, and they are launched into the liquid. And some time ago, we have studied them very carefully using fluid-solid interaction finite element models, which are capturing the elastic phenomena in the material, in the solid, using elastic equations and the Navier-Stokes equations for the liquid. When you do that, you get a lot of results just telling you what could happen, and you then ask yourself some of the methods I will show in the next few slides. But right now, I show you some experimental results on a lithium niobate substrate. So you have before streaming and the after streaming. You can make nice movies. You can see it getting removed. The signals here, it's very green on the screen, as not as nice here, but the pattern becomes very clear, showing that all this brown stuff, which is BSA, and then other proteins, you can remove them through the acoustic streaming phenomena. So by combining them, this quantifies by defining a power dose, RF radio frequency power dose, which is the milliwatts seconds, and you go and look at the intensity, and you can pictorially see that you can remove proteins that are non-specifically bound, and if you hit with hard enough energy, you can remove the specifically bound proteins. Remember, at the moment that lithium niobate I mentioned is a very high high acoustic coupling device. That means you can input energy quite easily, but I will show you in the next graph. Actually, that may be the one. This is the quartz. Quartz also, you can see this much more recent results, much starker removal using the, you can rinse all you want, but if you use this acoustic energy, you can remove the interfering proteins quite well, so you can see your patterns well. So why would you want to remove it? It's pretty obvious. You can look at, here are some controlled experiments that show what happens when there are organic acids, like you would in the real bodily fluids like blood, urine, and so forth. What would happen, and then some blocking, even if the protein you are putting in is stuck, and of course there can be overlapping spectra from proteins, other proteins that are in the bodily fluid that may autofluoresce. So I mentioned the model. I'll go through a few slides very quickly, but not to give you details of the model, but to just tell you that over years when we worked with the model, we are now convinced that we can actually quantitatively look at the energies that are needed and the displacements and so forth. So the next few slides show you that the finite element model produces some of the profiles we want, like the velocity profiles and the streaming profiles, streaming velocities, interfacial stresses, and you can study the parameters which affects this behavior, and you start looking quantitatively what kind of things happen. And of course, you cannot simulate a full device, but you can map it quite well by scaling. So these three graphs show you that fluid properties, for example, we have now done some calculations using non-Newtonian fluids, and finally tried to figure out a mechanism for the removal, adhesive forces, when we calculate all these different forces. So in summary, we have a mechanism that tells us how this works. The body forces, which are actually rather small in the quartz type devices, they are removing the protein from the surface, and so we have a multi-scale model in which we can look at the amount of interaction between the particles and the surface in terms of van der Waals and such forces. So, and you can see the streaming forces that are quantitatively calculated, drag and lift forces, to prevent the reattachment. So a very simple mechanism by which this streaming works. So the third part of what I mentioned, the second thing the surface acoustic wave device would do for the sensor would be mix. So here you can see the incubation time for a particular experiment. It would take maybe 60 minutes. It could take hours. It sometimes, in some cases, many hours. So that's why ELISAs can take a long time. The protocols are long. But in our case, we can see it is 60 minutes. But if you put this wave, surface wave, to mix it in without the surface acoustic wave, it's still in this region. That means it's the attachment is not as good. And now if you mix it with the SAW for 10 minutes, so the 10 minutes would imply from an hour to 10 minutes a factor of 6. So you can quickly incubate because of that recirculating motions that are caused. So this quantifies it. So getting to 1 would be what you want to see. So it takes you 30 minutes and 60 minutes to get to 1, whereas if you do 10 minutes with the SAW device. And so you can combine these two phenomena on a single device. We have shown some results here with silver cubes to get to about 1 nanogram per milliliter, which is typical of marker concentrations. We are looking at some proteins like BCL2 is a protein we look at, which is a marker for the ovarian cancer, as found out it's in the range of 1 nanogram per milliliter or less actually. And so we can show that from the acoustic streaming phenomena we can eliminate a lot of false positives, because one of the things about a biosensor is how much interference you have, how your signal's not coming to what you want to see, and as a consequence you get false positives. So that hopefully is reduced and mixing speeds up the process. So we have to now optimize these things for specific biomarker detections. So that's where we are. In the process we feel, of course, some microfluidics will allow us to build a device with some chambers and so forth to clean out some electronics and microfluidics, but this is the one which is really the tough one, because right now we are putting the silver particles on the surface through spinning. It's not the best way. I have had a colleague at Argonne Labs make some calculations, and he tells me with his machine to do a device like I would like, it's going to be 72 hours on the E-beam. I'm not going to do that. The techniques like what Aaron presented are what we need to do this, to get a point of care sensor. So I think I'm very hopeful. Very simple ideas can be like this, can produce a biosensor, I think, in a relatively short time. So I'd like to thank the National Science Foundation, which has given a grant to work this out, and then an I-Core grant to move this to industry, and some people from the medical school. Answer any questions.